This is the second applications of Bayet and Sabbat law. And in this application, we shall see about the magnetic field on the axis of a circular current carrying loop. So here we consider a circular loop carrying a current I, and this loop, it is having a radius small a. Now this line CP, it is the axis of the loop. Here I want to find out how much is the magnetic field at this point P. So for that, just like before, we will divide this entire circular loop into small elemental length. So first I will consider at this point O, which is above, I will divide, right? Let's say this is the small length dl. And this small length dl, right, it has got some direction, which is actually, right, this plane of the loop in this case, it is perpendicular to the plane of the boat, like this, like this. Now this is my dl, and this is my line PO. So the angle between PO and this current element dl, it is 90 degree. So therefore, if you consider this current element dl in this case, then I will get the small magnetic field at a point P. So the small magnetic field at a point P due to this current element IDL in this case, it would be dB equal mu naught upon 4 pi IDL sine theta upon, what is the distance between DL and P? It is S, so S square. But this theta here, it is actually the angle between this DL and S. So as I said, the angle between DL and S is 90 degree. So therefore, instead of theta, I will write sine 90. But this sine 90, it is equals to 1. So I'll rub this. I will write is equals to 1. So 1 times IDL will be just IDL. So this is my equation 1. Okay. So this dB, it is the magnetic field at the point P due to this current element dl. Similarly, if you consider the magnetic field at the same point P due to another current element dl dash. This dl dash, it is actually opposite to dl. So the magnetic field, right, at this point P due to this dl dash, again it would be dB dash equals to mu naught upon 4 pi I dl upon, okay, if this distance is s dash square, then I'll write s dash, then I'll write s dash square. This is my equation number 2. Okay. Now looking at the directions of these two small magnetic field, dB and dB dash. The directions of dB here, it is acting along PQ, which is perpendicular to the plane containing this vector S and dl. Similarly, the directions of dB dash, it is along PQ dash, it is along this direction, which is also perpendicular to the plane containing S dash and dl dash. Now, these two vectors dB and dB dash, they can be resolved into two vector components. One is along the horizontal component and the other is along the vertical component. Okay. So if this angle, it is phi, then let us say that this angle also is phi dash. So then, because this dB, it is acting along this direction, so when you resolve into two components, one you have to take along x, another along y. So it means this angle also is phi. Similarly, if this is phi dash, this will be phi dash. So for this, I will leave you as a homework to verify by yourself about this angle. How do we get this angle as equals to phi? So that is your homework. Because I cannot teach you here everything, because it will consume a lots of space, right? So sometimes you need to do your home assignment also. Okay, so if this is phi, then if you resolve this dB into two vector components, then you will get along x-axis, it will be dB sine phi, and along y-axis, it will be dB cos phi. Similarly, if you resolve dB dash along x-axis, you'll get dB dash sine phi. Along y-axis, you'll get dB dash cos phi. Now, look at this figure. Look at these two equations. We see that the magnitude of dB and dB dash is the same. Okay, we have mu naught upon 4 pi I dl s square. Over here also we have mu naught upon 4 pi I dl upon s dash square. So because from symmetry, right, this s and s dash, right, they are at a same distance. Okay, they look alike, so therefore the distance between s and s dash, it is the same. So if s and s dash is the same, which means equation 1 and equation 2, right, it is equals to each other. Okay, so if you consider in this way, like any two current element in the diametrically opposite direction, then you will always find that this component dB cos phi with dB dash cos phi dash will be equal and opposite in direction. So in that case, they will be cancel out each other. So however, the only component which remain uncancelled here, it is the x component, that is dB sine phi and dB dash sine phi. So this dB sine phi and dB dash sine phi, they are acting along the same direction. So these two components, right, they will add up and they will contribute to the total magnetic field at this point P. So therefore, the total magnetic field at a point P now, it can't be written as B, and this B, it is equals to the integrations of dB sine phi. I hope this is clear. Okay, or B is equals to integrations of, how much is dB? Mu naught upon 4 pi I dl upon s square sine phi. How much is sine phi? Look at this triangle. Sine is equals to A upon S. So A upon S. Alright. And the limits of integrations on the right hand side in this case, right? Because mu naught upon 4 phi is constant. So I'll take it out. I is constant. I'll take it out. A is constant. I'll take out. S square with S become S cubed. So I'll take it out. So the only thing which will be left inside the integration is dl. So when I say dl, it means you are integrating over the circle or the circular loop. So for that, the limit will goes from 0 to 2 pi r. Okay. So B is equals to mu naught I A upon 4 pi s cubed. And if you integrate this dl, you will get L. And after substituting the upper limit and lower limit, then it becomes 2 pi r. Now this pi from the numerator and denominator cancel. Not 2 pi r, this is actually 2 pi a because the radius is a. I made a mistake, sorry. This is 2 pi a. Okay, so my b here, okay, even this 2 and this 4 also can be cancelled. So my b becomes mu naught I. A with a is a square upon 2s cubed. Now how much is s? Again, look at the figure. This s, if you consider this right angle triangle, then s by Pythagoras theorem, s square is equals to a square plus r square. Or just s, it is equals to a square plus r square to the power half. So if s is equals to a square plus r square to the power half, then I will say that this b here is equals to mu naught a square upon 2 instead of s cubed. Now I will write a square plus r square to the power 3 upon 2. So I'll name this as equation 1. So this equation 1, it is actually the equation, sorry, this is equation 3 because we already have equation 1 and 2 above. So this is equation 3. So this equation 3, it is the expressions for the magnetic field on the axis of a circular loop carrying a current. Okay. Now, from this equation 3, I will draw 3 special cases. So let us see about those special cases here. The first case is when point P is at the center of the loop. When P is at center of the loop means is at C. If this point P come here, it means R will be 0. So here R is equals to 0. So when R is equals to 0, your equation 3 becomes how much? B equal mu naught I A square upon 2 and then A square. So this R is 0, that means this will disappear. You'll have to the power 3 by 2 with this. So this with this cancel. So which means B is equals to mu naught I, okay, A square upon 2A cube. So again this A square with A cube cancel. You'll get mu naught I upon 2A. So if you remember in my previous lecture video, I have explained about the magnetic field at the center of a circular current carrying loop. It is equals to mu naught upon 2R. But in this case, the radius that I'm considering here is A. But before in my previous lecture video, the radius I'm taking it is small r. So that means the results is the same thing. Okay. So we are getting right from this general expression equation 3, we get the special case right when the point P comes to the center of the loop. Okay. My second case here is when this point P, let's say it is lying at a very far distance from the center of the loop. Okay, so second special case is when P is very far from the center. So when the point P is very far from the center, at that time the small r becomes so large compared to the radius of the loop. So in that case, this A square, right, can be neglected compared to R square. So therefore, if you neglect this A square compared to R square, this equation 3 becomes B equal mu naught I A square upon 2. Now you have neglected this A square, so you'll get only just R square to the power 3 upon 2, which means mu naught I A square upon the square with this cancel, which means 2R cubed. So this is my equation for the magnetic field, right, on the axis of the loop in which the point P, it is very far from the center of the loop. So that is my third special case. And the fourth special case here is when the point P, let's say it is at a distance which is equals to the radius of the loop. That means when this point P, let's say it comes here, and this point, this distance from here to here, let's say it is same as the radius. So my third special case is when P, okay, or I can say when R is equals to the radius of the loop. When I say R is equals to the radius of the loop, that means this point P, it comes here, in which the distance is equals to the radius of the loop. So in that case, my magnetic field at this point from equation 3, it becomes B equal mu naught I A square upon 2. a square, instead of r also I'll write a square. So we get a square plus a square to the power 3 upon 2. And this is equals to mu naught I a square upon 2 a square plus, okay, this is 2a square to the power 3 upon 2. Now, what I have to do here is, I have to take the cube, of the number different, okay, in the bracket. Which means I will get b is equals to mu naught I a square upon 2 times, this is 2 to the power 3 by 2, okay, times a square to the power 3 by 2. So now this 2 with this 2 cancel. Then what you'll have here is, okay, I'll drop first. B is equals to mu naught I. This a square now with a cube can be cancelled. So mu naught I upon this 2 and this 2, this is power 1. If you combine, you'll get 2 to the power 5 by 2. Okay, so this is how we can draw, or we get the magnetic field at different positions of the point P. Alright, so I hope this is clear. Okay, do I make any mistake? Okay, yes, I think here, because this square with this cancel, so we left with a, so don't forget the number a here. Okay, and after that, what else we have? Okay, no more. Okay, so this is all about the magnetic field at different points of the axial line. Okay, when the axial line, it means it may be at the center, it may be at a very far point from the center, or it may be at a distance which is equivalent to the radius of the